Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to The Naked Scientists with me, Ben Valsler, and with Helen Scales.
Hello.
This week, we're going to find out how Margaret Thatcher's face can tell us how monkeys recognise other monkeys' faces, what sharks have in common with serial killers, why dolphins are a bit like jet fighters, and we find out what's going on in the mind of a pigeon as it finds its way home. Helen.
All lots of zoology fun, but we're also looking today at new ways of putting a tiger in your tank. We'll find out how the life that lives in your pond could help us make eco-friendly biodiesel, and how new types of batteries help to power electric cars for further than ever before without running out of juice. Plus, how clever engineering will help us create a new breed of carbon-neutral electric and hybrid racing cars, which will be able to compete with the fastest internal combustion engines.
It's geared up now to do 75 miles an hour top speed. That's because we're going around a fairly twisty-turny track. If we geared it to its full potential, it would be topping 300 miles an hour.
That's impressive.
Yes, impressive, not feasible for the racetrack, but shows that this technology can do some fairly impressive stuff.
A far cry from the golf buggy image that many people do have of electric cars. We've also got our question of the week. We'll be finding out how efficient your new car must be in order for you to make a carbon saving when scrapping your old banger. So if you've got any other questions for us, please get in touch. The address is chris@thenakedscientists.com.
The Naked Scientists Podcast. Powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
We've got lots of news from the animal kingdom today, as is Helen and my wont. And in particular, research from Emory University shows that we and our ancestors have been recognising faces in much the same way for at least 30 million years. By watching how rhesus macaques respond to a well-known optical illusion called the Thatcher effect, Professor Robert Hampton and colleagues were able to determine that these monkeys, just like us, recognise faces not because we compare them to an idealised picture of a face, but because of the relationship between the different features.
So what is this Thatcher effect?
Well, it's an optical illusion that many of you will have seen before. I've actually got a picture of it here as well, Helen. It's created by taking a picture of a face, and then you cut out the eyes and the mouth and turn them upside down.
OK, we've got a picture here of a chap with quite long hair, but all right. So on the top here, we've got ones where the eyes have been cut out and turned round, is that right?
Yes, the top ones are the Thatcherized ones. Now, if you look at that with the whole head upside down...
So his head is upside down, and that looks fine to me. It looks fairly normal.
Quite reasonable, doesn't it?
Yeah, that's certainly nothing wrong with that, yeah.
But then if we turn it round...
Oh, my God! It looks very different. That's so strange. It just looks completely different when the face is the right way up, but the eyes and the mouth are upside down. He looks very evil at me.
It's quite grotesque, isn't it? It's clearly not right. And it's thought that this effect works in humans because we perceive faces as a configuration rather than as an image. So this makes us more sensitive to differences in configuration, which means that we can recognise individuals. So the distance between the eyes, the angle between the edge of the lip and the edge of the eye, those sorts of things. Instead of storing it as a picture, we store it as those set of rules.
And I have to ask, why is it called the Thatcher effect? Do we have any idea of that? She doesn't have her eyes upside down, did she, Margaret Thatcher?
Well, actually, it was first discovered using a picture of Margaret Thatcher.
Oh, I see.
And I first saw this with a picture of Elvis, but it's obviously not called the Elvis effect.
Excellent.
And who'd have thought that Margaret Thatcher would have been terrorising people for all these years?
Indeed. And how on earth did they go about testing if monkeys respond the same way? They don't go, oh, that looks awful. How do you actually do that?
Well, the idea is that if the monkeys react like we do to these Thatcherised pictures, then that proves that they also see faces as a configuration rather than as an image. So to test it, the researchers showed some rhesus macaques some pictures of other rhesus macaques' faces.
Not Margaret Thatcher?
No, not Margaret Thatcher.
Okay.
Some of them were normal and some of them were Thatcherised, and they monitored how much attention they paid to each set of images. So once they'd got used to being shown photos, they actually showed no more interest in upside-down Thatcherised images than they did in upside-down normal faces, or in fact just normal faces. So they weren't really really paying attention. But as soon as you turned it the right way up, so we get the reaction that you had there of sort of disgust, they paid a lot more attention to them then. Now that suggests that they do detect faces as a configuration, and that they obviously think there's something going on there that warrants their attention. And that suggests that this configurative way of looking at faces must have evolved at least 30 million years ago in our common ancestor with the macaques.
And how about other animals? Do we know if anything else has the same face recognition ability?
Well, not many studies have been done, actually, but previous studies have shown that Thatcherized images have no effect on pigeons or on baboons, and the baboons may seem to contradict this, the results we've got here with rhesus monkeys. However, the baboon study was published back in 2008 in the American Journal of Primatology, and the animals were extensively trained with actually a small set of images. So they may have stopped responding to them as faces and started just looking for clues in the images, and so it may not actually represent the same spontaneous effect that we just heard from you. And the researchers said that this direct evidence of configural face perception in monkeys, collected under testing conditions that closely parallel those used with humans, indicates that perceptual mechanisms for individual recognition have been conserved through primate cognitive evolution.
That sounds fantastic, and does explain why this chap in front of me does look so terrible.
There is a picture on our homepage right now if you want to go and have a look on thenakedscientists.com and just have a look at the different faces and see which ones look normal, which ones look grotesque, and then just sort of turn your head upside down and see what happens.
It's pretty amazing stuff. Anyway, as we said, I'm going to stay in the animal world with my first story about serial killer sharks. Scientists have shed light on how those iconic ocean predators, the great white sharks, go about catching their prey. And it turns out that they have something in common with human serial killers as well. And it turns out that they actually lurk around in spots that don't necessarily guarantee them the best chance of encountering a seal, which is their favourite food, but they also try and minimise the chances that the seals will spot them before they launch an attack. And they also take into account where other sharks are as well.
How on earth do you study all of that? You need to know surely where all the seals are, where all the sharks are, and it's all underwater, so it's not like you can just watch from above.
Well, actually, you can. I mean, the study, which was led by Neil Hammerschlag, a PhD student from the University of Miami in the US, and they took advantage of the way that great white sharks, in particular in False Bay in South Africa, attack their favourite food, the Cape seals. And what they do is they target young solitary seals who are at the surface of the water, and at low light levels, so in the morning, perhaps in the evening, they lurk around on the sea floor and they stalk up on an individual seal before ambushing it with a sudden vertical rush that propels both the shark and the seal sometimes out of the water. You might have seen that on some TV documentaries. It's quite extraordinary. They can actually leave the water completely because it's such a big burst of energy.
It's one of those photos and one of those shots that every wildlife photographer that works on the seas must want.
Absolutely, indeed, yes. And you might say, well, that's a bit of a strange way to attack. It's a lot of energy required in that. But it's the best strategy for sneaking up and delivering a single fatal bite to those seals.
So what, they just watched for these particular attacks just by staying on the surface, and then... So what does it tell us something if you know where they took place?
That's right, indeed. They saw 340 shark attacks from just boats on the surface, and then they mapped those out with GPS units, so they knew exactly where they were. And then they analysed the data rather cleverly. They teamed up with a criminal justice expert called Kim Rosmo, and they used a set of computer software that's been developed to study geographic patterns in human crimes, and that includes terrorist attacks and serial killers. And it's a process called geographic profiling. And by looking at where particular crimes, a series of crimes takes place, say murders or arson, terrible things like that, the software actually narrows down anchor points, which are possibly where this criminal lives, maybe where they work, but it tends to really pinpoint where they're actually having that activity. So Hammerschlag and his colleagues put the same shark data into this software that's hunting out human criminals as well.
But I guess the real question here is, do sharks behave in the same way that human serial killers do?
Well, actually, they kind of do. We talk about these anchor points, and it's the bigger, older sharks that seem to have these particular areas that they hang out in, and they, in fact, are the best places to be to attack the seals. It's about 100 metres away from where the seals congregate, so they don't hang out right where the seals are, because they'd scare them away, and that'd be no good at all. But they sort of lurk around the edges and then pick off individual seals that will stray away from the main group. And the interesting thing is, when they looked at the differences between smaller and larger sharks, it's the smaller, younger younger ones, then actually they hunt over a much wider area and they don't get to use these really good spots, these good anchor points that the big sharks use. And that really hints that as they gain experience, as they get older, the sharks learn how to refine their search patterns, and also they're probably more aggressive and they can keep out the little ones from those best hunting spots. So it's really kind of helping us to unveil some of the mystery behind these incredible predators and just how they go about catching their prey. And perhaps it helps us understand a little bit more about where we shouldn't hang out. I mean, where we shouldn't go surfing and swimming, anywhere near those anchor points, I think, where those great white sharks tend to hang out.
It's worrying to think of sharks as honing their killing abilities like that. And now I'm going to go to an animal that is far, far less dangerous. In fact, the worst thing that these are likely to do is poo on you as they fly past.
I certainly don't like them very much.
I'm sure that's happened to a lot of us. And this is actually a first study of its kind, and researchers have recorded what's going on in the humble homing pigeon's brain during flight. Now, writing in the journal Current Biology, researchers at the University of Zurich wanted to know if familiar landmarks could be associated with changes in brain activity. So the exact methods that homing pigeons use to find their way home are still actually a bit unclear, even though we've had years to study this. There's some evidence that they rely on the sense of smell. There's some suggestion that they rely on the position of the sun, the Earth's magnetic field, or familiar landmarks in order to track their way home. But because they're so versatile, it makes it really difficult to study, because even if you know exactly where they've been, it's really hard to say what method they're relying on at any particular part of the journey.
So what was this study doing that was new to help us understand more about this?
Well, they actually fitted the pigeons with a very small electroencephalogram, or an EEG. It weighs less than 2 grams, so it wasn't really a problem for the pigeons. And that records electrical activity in the brain. And they combined that data with GPS data for their flight paths. And so they were able to map brain activity onto geographical areas of interest. The pigeons were monitored as they flew from a release site all the way back to their loft.
That's incredible. So they're carrying not only a GPS to track them, but they're looking inside the brains at the same time. So what did the researchers find out from that?
Well, there were 2 distinct levels of brain activity they found. There was a middle frequency response, which happened when the pigeons were looking at something, and they checked this as well with pigeons in captivity. And there was also a high frequency brain activity, which seemed to correspond to familiar objects. And so this suggests that it's sort of additional thinking. So you've got the one set where they're seeing something, and then this higher frequency where you've got additional cognitive processing going on. Now, these results mean that we can use the record of brain activity to identify the areas that are important for pigeon navigation. And we would never have been able to determine them necessarily from GPS data alone. So this gives us a real insight, and a unique insight, into how birds navigate in the real world. Now, interestingly, there were a few bits of the journey where they found this unexplained brain activity, and this is the sort of thing that can really kill off a project. I don't know why we picked up this signal. And it seemed to coincide with places that were so close to their loft that they couldn't possibly be useful for navigation. There was something else going on. The researchers called it a riddle. They call it a riddle in the paper, which is a nice thing to see. And it's one that they only solved when they went to actually visit the sites that the pigeons were looking at. One was a farm, and the other one was a barn, and both of them contained large colonies of feral pigeons. So clearly all of these other pigeons down there had caught the study pigeon's attention, perhaps looking for their mates or perhaps looking for their next girlfriend.
Excellent. That is incredible stuff indeed, to follow what's going on inside a pigeon's brain as you let it fly around. That's fantastic stuff. Well, finally this week, I'm going to stick once more to the ocean world. Sorry about that. But if you could be any animal in the world, I bet there's lots of you out there who would choose to be able to swim through the sea as skillfully and effortlessly as the dolphins. I certainly would love to be able to do that. And now scientists have uncovered the secret behind some of the dolphins' amazing aquatic acrobatics. They have flippers, it turns out, that work in the same way as a delta wing, and those are the characteristic triangular-shaped wings on fighter jet planes, and also on that amazing feat of 20th century engineering, Concorde.
OK, so going back a bit, we've already had people sat on boats watching sharks jumping out of the water. Did they do the same sort of thing again? Did they go out and watch dolphins in the wild?
No, not for this study. They stayed quite dry, in fact, and the research team, led by Lawrence Howells and Paul Webber from Duke University, scanned the shape of 7 different species of dolphins' fins. They included the Amazon river dolphin, the pygmy sperm whale, and the striped dolphin. And what they did actually is they took fins from dead dolphins. They didn't kill any dolphins for this study, don't worry. They were already dead. They were either museum specimens or animals that had unfortunately been stranded on beaches. And they put these inside a computer tomography or CT scanner, and that produced detailed three-dimensional pictures of those fins. They made models based on those pictures and then put them inside flow tanks to see how they performed.
Oh, OK. So once they put them in a flow tank, what did they actually want to measure?
Well, it's quite clever, actually. They mount these flippers onto a set of special weighing scales, essentially. And what that does is measure two different forces that are really important in flying, because, in fact, dolphins are essentially flying underwater, not swimming. And that's the lift and the drag generated by the flipper at different angles of attack. So what's really going on, the secret behind flying, is the shape of the flippers, or the wings, if you're a bird, and that they're tear-shaped. So as air or water flows over the wing, it has further to travel over the top than under the bottom of the wing, and it speeds up, and essentially this means it creates lift, pushes the wing, and that's pushing the wing or the flipper upwards. And to be stable in water, the fin needs to be able to generate enough lift to overcome the drag, and that's a force that goes backwards, trying to push the fin backwards because of the friction that it encounters with water.
And this really does sound like we're talking about birds, doesn't it? We're
It
talking
is,
about
it's
lift
amazing,
and
yeah.
drag and wing shapes and so on. But surely in water the problem is going to be the amount of drag, much more drag than air. So how much sort of drag and lift are they measuring in the different flippers?
Well, absolutely. Well, water's more viscous and so on, so it's more difficult to push through it. If you try to wade through water, you know that's very different to sort of walking just on land. And in fact, it was the difference between the different species that was interesting in what they found here. Some species of dolphin and whale seem to perform much better than others, and it's all based on the size and shape of their fins. And it was in fact the familiar bottlenose dolphins that generated the greatest amount of lift, while the least efficient fins actually belonged to the harbour porpoise and the Atlantic white-sided dolphin. And some of the dolphins have flippers that act in a very similar way to the triangular swept back wings of fighter jet planes, and that's the sort of configuration that leads to additional lift through something called a leading edge vortex, and that's essentially a swirl of air around the front edge of the wing, and that helps to create even more lift, and why I think planes like Concorde could fly so fast through the air. And really this all goes to help explain just how some of the dolphins can swim incredibly quickly indeed, up to 20 miles an hour, and they were speeds that until now really seemed to be quite theoretically impossible because of all that friction and drag from the water. But now we have a little bit more of an idea of how those marine mammals keep swimming against it, and how they do. It's really rather fantastic, and yes, I wish I could swim like a dolphin. That'd be wonderful. Can I have that, please?
So the next time you see things like dolphins and they look like they're flying gracefully underwater, you're actually a lot closer to the truth than you thought. Excellent. There's also been some fascinating news this week about Enceladus, one of Saturn's moons. There's evidence for a liquid ocean beneath the icy crust, and this could well have all the ingredients required for life. Really exciting news.
And I've been looking at another study here which could provide hope for people who suffer from appendicitis, which is a new test looking at proteins in the urine, which can really help nail down whether or not they should have their appendix out, because appendicitis is the top reason why kids go to hospital, and quite often they have their appendix out when they don't need to, or they have them out a bit too late after they've already ruptured, and that can be really dangerous. So you can read about that and lots of other science news stories on our website at thenakedscientist.com/news.
Distilling the best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
You're listening to The Naked Scientist with Ben Valsler and Helen Scales. Don't forget you can also listen to us online anywhere in the world, or even out of this world in Second Life.
Coming up, we find out how a carbon-neutral car could compete with the best big fat muscle cars around, and how you could be putting algae into your petrol tank.
But first, we've a power-related kitchen science for you.
For this week's Kitchen Science, we're plugging in to the science of batteries. Now, Dave, what do you have for us?
Well, this week I thought we'd do a little experiment with some batteries. All you want to do is get a couple of batteries, ideally one of the old-fashioned zinc carbon batteries, and some other types of batteries. You want at least two of each. Put some in the freezer, get them nice and cold, and keep other control batteries outside of the freezer. And then we're going to compare them to see how they work afterwards.
Batteries generally are fairly hygienic, but is there any risk that we might contaminate food with it?
There's a small chance you might cause a battery to leak, so you probably want to put the batteries in like a plastic bag or a little container or something, so you don't ruin your lovely steak for tomorrow night.
Battery-flavoured steak. So, before we really get into this, how do batteries actually work?
Well, batteries are essentially a pump for pushing electrons around a circuit. They work by releasing chemical energy and using it to push these electrons around the circuit. They work with a type of chemical reaction called a redox reaction. These are things like rusting. It's basically where one kind of molecule or atom loses some electrons, another one gains some electrons, and this releases some energy.
So the chemistry inside basically just involves shuffling electrons around. And this is why when we plug them into our MP3 player or our torch or something, that's why it can push electrons around a circuit, and then they do work for us, lighting the bulb or playing our podcast.
Yes, in a reaction like rusting, both halves of the reaction are happening in the same place. The iron is losing electrons and the oxygen is gaining electrons. They're right next to each other, so we can't do anything useful with that energy. But the people who design batteries are very cunning. What they do is they split this reaction into two halves. So, for example, in a dirt cheap zinc-carbon battery, on the negative electrode, you've got zinc losing electrons onto the negative electrode. And on the other side, on the positive side, you've got ammonium ions gaining electrons to form ammonia. Now, these reactions will keep on going for a while, so the negative terminal will get more and more negative, and the positive terminal will get more and more positive, until the energy it requires to push another electron onto the negative electrode or take another one off the positive electrode is so much that it's more than the energy released by the reaction.
And that would mean that if it's not energetically favourable, the reaction will stop.
Yeah, that's right. And that's why when a battery isn't plugged into anything, the reaction doesn't happen. It will just sit there for, in some cases, years and years and years without anything much happening.
Until, that is, you plug them into something.
Yeah, that's right. You've got a load of electrons squashed together at the negative side. They want to expand. So if you give them a route to do that along a wire, they'll expand through that wire and push themselves along the wire back to the positive end, forming electric current. As soon as the electrons get to the positive end, then the reaction can carry on, and you get a current running through the battery until you run out of reactants to drive it.
But there are all sorts of different types of batteries. Do they all use the same chemistry?
They use similar chemistries, but the subtleties are different because some batteries, like a car battery, you want to be able to produce a huge current when you start the car, but you're not really worried about how heavy it is, so you can use really dense metals like lead, which are really heavy. There's not a huge amount of energy in a car battery for its size, but it can produce an immense current when you start the car. Hearing aid batteries you want to last for a very long time, but only produce a very small current. So people who design batteries play with different chemistries to produce the kind of battery you want.
OK, so that's fairly basically what batteries are and how they work. But why have you put them in a freezer?
Well, knowing that a battery is run by chemical reactions and that chemical reactions are affected by temperature. For example, if you have a lump of wood, you can leave it in a room at 20 degrees C for thousands of years and not a lot will happen to it. But if you heat it up to 500 degrees centigrade, it ain't going to last very long. It's going to burn. So I thought we'd see how temperature affects various different types of battery.
And you have a multimeter here to test it with. Now, I've used these before. They can measure resistance, voltage, current. What are we actually going to measure?
So at the moment, I've got it set up to measure voltage. So that's how hard the battery is pushing the electrons around the circuit.
Well, let's have a look at one of your batteries. You've got a zinc-carbon battery, and it's at room temperature. So let's have a look and see what the voltage is.
It's producing about 1.7 volts at the moment.
It actually says on the side that it's 1.5 volts, so obviously getting a bit of extra free energy from it. But is that the voltage that we'd see if we were actually using it?
It all depends on how much current you take. For example, I can plug a light bulb into this now.
So we still have it attached to the multimeter, so this will now tell us the voltage it's drawing whilst at the same time lighting up a light bulb. The bulb is lit, and it says 1.53 volts, so clearly we've lost some voltage.
That's right. If you don't draw any current from the battery, it can keep pushing electrons onto the negative terminal away from the positive terminal for as long as it likes, and it will slowly reach the maximum voltage it can produce.
And the multimeter isn't pulling any current?
Yeah, that's right. But as soon as you start drawing current, then the voltage you can produce is limited by how fast the battery can push electrons around. So the actual voltage it can produce is reduced.
How about the frozen one?
Well, we can give it a try.
So this has come fresh out of a freezer. It's a very cold battery. And so now, with a frozen battery, we're reading a voltage of, it's 1.7 volts. So even though it's been frozen, it doesn't seem to be any different.
But we can try it with the light bulb on again.
Oh, we're seeing 0.88 volts, and the light bulb is hardly lit at all. So with no current being pulled, we're still seeing the maximum around 1.7 voltage. But with the current being pulled, the frozen battery can't handle it at all.
Yeah, that's right. We've slowed down the chemical reactions by cooling down the battery, which doesn't affect the maximum voltage it can produce, but it does affect how fast it can produce current. So it reduces the voltage as soon as you start drawing a current with a light bulb.
OK, well, that's one type of battery. Are other ones designed to overcome this problem? Can other ones work in really cold environments?
If you reduce the temperature, you're going to reduce the maximum amount of current that any battery can produce. However, some batteries can produce more current to start off with than others. For example, a rechargeable battery can produce a lot more current than one of these zinc carbon batteries. So for the same light bulb, it's not going to be affected nearly as much. But if you tried to power a radio-controlled car with it and draw lots of current, it's not going to work as well.
But surely there are some conditions where batteries are really put to the test. For example, Arctic missions or out in space. How do we get around this problem there?
It is a big problem on space missions because if your batteries get too cold, they're not going to produce enough current, and then your computers stop working, and then you've got a dead spaceship. So they do actually have to heat up their batteries and stop them getting too cold. So they actually have little electric heaters powered by the solar panels to keep the batteries warm and stopping them dying.
OK, so does this mean that if I bulk buy some batteries and try and get a sort of cash and carry discount on them, I should then keep them in a freezer to make sure that they last longer?
If you have a battery just sitting there not doing anything, the chemical reactions do happen very, very slowly. Basically, they will discharge on their own just sitting there because little currents can flow in places where they shouldn't really. And cooling them down will slow this down, but it's not a very big effect. Some people think it's a good idea, but apparently it's not a very large effect, so it's probably not worth it.
So there you go. You may as well just store your batteries on the shelf. Or, even better, don't buy so many of them in the first place. That's all we have for this week's Kitchen Science. We'll be back with more next week.
So, freezing a battery slows down the chemical reactions inside and reduces the power you can get from it.
I do love doing kitchen science. It's always so
You
fascinating.
have so much fun.
After last week's experiment, where we demonstrated how flowers take up water by using food colouring to make a white flower multicoloured, we heard from Ashley Dunn in Australia. She sent us an email saying, I listened to your podcast with regards to changing colour of flowers using food colouring. My granddaughter and I picked a white rose and did the split stalk experiment. This is where you split the stalk up the middle, put one half in one colour and the other half in the other colour. And she said that we invited us to send in photos, so she sent us their one and only attempt. So that's Ashley Dunn, and Emma is her granddaughter, and they've sent us a picture. We've put it onto the website. You can find that at thenakedscientist.com/kitchenscience. I must say, it's actually probably a bit better than our photos of it.
It's gorgeous. It really is. You have to check it out. I've got it right here. It's very pretty indeed.
Very pretty and very colourful.
And very colourful. And you can clearly see the two sides, the blue and the red, coming in there. It's fantastic. Yeah. And also on our forum, Chemistry Form said he tried it with celery and ended up with half blue, half orange celery. And maybe that's a way of making it colourful to encourage children to eat it. But I'd say definitely just use food colouring, not any kind of ink. That might be not so good. Food colouring in your celery, definitely a way of making it more colourful. But if you would like to let us know about your own science experiments, or if you've got something you think we should put our experimental touch to, then do get in touch. The email address is chris@thenakedscientist.com.
Laying the facts bare.
I say.
The Naked Scientists.
Well, electric and hybrid cars do have a bit of an image problem. Many people think they're a bit slow, a bit goody-goody, perhaps a bit worthy. But this week, Mira Sinthlingham visited Imperial College London to find out how electric and hybrid cars could soon rival modern petrol-hungry muscle cars.
This week, I've come to Imperial College London to meet the scientists and engineers of Imperial Racing Green, a project that designs electric and fuel cell hybrid cars for the racetrack. And with me is Dr. Greg Offer, the academic project manager. Now, Greg, firstly, what are electric and hybrid vehicles? How do they work?
An electric car is powered by batteries. The batteries need to be charged by electricity, which you take from the grid. Every building in this country has a power socket, and you can charge the batteries from the power socket. The batteries then power an electric motor, which drives the wheels. The main problem with this is actually the amount of power you can get from the socket. Most domestic circuits are limited to 13 amps, so it would take you quite a few hours to charge your battery.
And how about a hybrid car?
There are two types of hybrids. The first is what I would call a first-generation hybrid, which is like a Toyota Prius. That's an internal combustion engine-powered vehicle, which has an electric motor and a small battery pack to assist the combustion engine. Second-generation hybrids are the more interesting. This is an electric vehicle, which is a battery powering an electric motor powering the wheels, and it then has an internal combustion engine, a range extender, to assist the electric vehicle when it's needed, but you can still run it as an electric vehicle.
Now, why would an electric vehicle need assisting?
The main Achilles heel of electric vehicles nowadays is the batteries. And to deliver the range that consumers are used to, you have to have a lot of batteries, which means expensive, weight and size. So in order to overcome some of those problems, we use a range extender.
Now, what are the advantages then of these hybrid and electric vehicles over an internal combustion engine vehicle?
Okay, the principal advantage of the battery electric vehicle is efficiency. Even now, with the way that we currently generate our electricity in this country, which is predominantly through coal and gas burning off, the electric vehicle is still going to produce roughly 50% less CO2 emissions per mile.
Are there any advantages to the actual performance of the vehicles?
Yes, electric vehicles will perform better in terms of acceleration. The electric motor is much more efficient at low revs. In fact, you get all of your power from standing, which enables you to accelerate from the line much quicker. Combustion engines are remarkably inefficient and don't give you much power when you're accelerating. There's also some other advantages in terms of air quality. Combustion engines produce other emissions in addition to CO2, such as nitrous and sulfurous oxides, and those are currently governed by some quite strict regulations, which will be getting stricter and stricter. Electric vehicles don't produce any harmful emissions from the vehicle.
What do you think, then, the future of these types of vehicles are? Are we likely to see electric vehicles being used by everyone soon?
Pretty much every new car on the road within 10 years, I predict, will be electric in some form or another. And by 2030, they'll all be plug-in hybrids. And then once we get to 2030, we've probably met our emissions reduction targets. We need to reduce CO2 emissions by about 50% by 2030. We can do that with plug-in hybrids. The question is now it's about scaling up. It's about mass production. And it actually requires a lot of people. So training engineers is crucial. And this is what Racing Green is all about. We train over 100 engineers a year in electric and hybrid vehicle technologies. They can then go and work in these industries and actually become the engineers who help us build the future.
Dr. Greg Offer, the academic project manager here at Racing Green. Now, he mentioned that they're training up the engineers of the future, and I have one of these engineers with me now, and that's Aaron Kankuwala, who's the chief powertrain engineer for Racing Green. So tell me what you're doing with Racing Green, because you're actually adapting this electric vehicle technology and hybrid technology to make race cars.
Yes, very much so. Part of the stigma about green cars at the moment is that they're not very sexy, not very quick. So what we're doing is taking this technology and putting it on the racetrack. We're actually standing next to our current vehicle here, which is the third we've built, the previous two being go-kart-sized vehicles, and now this is a four-wheel open racer. It's about 1.5 meters wide by 3.5 long, fairly sizable, which will enter into the Formula Student Championships in July. Formula Student's been around for a long time, competition run by the Institute of Mechanical Engineers. It's predominantly IC engine cars, showcasing student skills in building these types of vehicles. For the last 2 years, though, they've allowed entries in a low-carbon class, and that's what we'll be entering into with our zero-carbon vehicle.
What have you had to do to this to adapt general electric vehicle and hybrid technology to make it into a race car?
Well, one of the biggest problems we had was weight. Race cars need to be very light, so they handle well and are very nippy around the track. Unfortunately, electronic components at the moment aren't built for race conditions. Most of the components we use on the vehicle are actually meant to sort of stand still in a laboratory and power sort of a generator for a while. Yet we're taking this technology off the shelf and making it perform around a track. And so we've tried to select the most lightweight components we can, giving us the best power-to-weight ratio on the vehicle.
So what are the advantages of using an electric vehicle over an internal combustion vehicle on a racetrack?
Electric motors actually have a distinct advantage over IC engine cars because they can produce their full torque from 0 revs. Another advantage is the ability to use regenerative braking. When an IC engine car brakes, a lot of energy is wasted in just heating up the disc brakes, whereas we can actually restore this energy that we've put down on the track back into our batteries and go further, faster for longer.
Now, this particular model is an electric car, but it uses a hydrogen fuel cell as well.
Yes, the primary use of the fuel cell on this vehicle is to produce extra power and also to extend the range of the batteries that we're using as well. With the fuel cell running throughout the whole race, we can actually go about a third more distance, which means we can go a third faster. Very useful and a very neat solution to overcoming the range problems that come with batteries in electric vehicles at the moment.
So have you had a go? Have you had a test? How fast does it go?
It's geared up now to do 75 miles an hour top speed. That's because we're going around a fairly twisty-turny track. If we geared it to its full potential, it would be topping 300 miles an hour.
That's impressive.
Yes, impressive, not feasible for the racetrack, but shows that this technology can do some fairly impressive stuff.
That was Aaron Kankiwala, Chief Powertrain Engineer from Imperial Racing Green, and before that Dr Greg Offer, the Academic Project Manager, showing Mira St Thillingham that electric and hybrid cars can be engineered to be on par, if not actually better, than the internal combustion cars we see today.
Reacting to the world's best science. The Naked Scientists.
You are listening to The Naked Scientist with Ben Valsler and Helen Scales. So far we've heard that electric cars have a great deal of potential, but they're held back by the weight, capacity and the expense of their batteries. So new types of batteries are actually essential to seeing more electric cars on the roads. Dr Andrew Loynes is the Chief Technology Officer for Atraverda, a company working with the University of Glamorgan, amongst others, and developing a new type of battery. Hi Andrew, thanks for joining us.
Good evening, Ben. How are you?
I'm very well, thank you. What's the problem with existing batteries? What's wrong with them?
One of the problems with batteries generally is that it's always some kind of trade-off, either between the operating performance of those batteries and their actual cost. Another issue, of course, is obviously safety. So the more power that you try and condense in a smaller space, then although it will give you more energy, it has the potential, if it isn't controlled properly, to cause issues in terms of safety.
I think we saw this a few years ago with a batch of laptop batteries which spontaneously combusted.
Indeed, and obviously the lithium battery industry is working extremely hard to get those issues out in the open and to understand the types of processes that they are having to go through in order to build the batteries safely.
And you're developing what is essentially a new type of battery. What's the difference with your battery compared to the ones we've heard about already?
Our battery is an advanced battery based on lead-acid chemistry. So lead-acid is basically safe, it is proven, it's been around for over 100 years, and it is almost 100% recyclable. So for every spent battery, you actually create a new battery out of it. What Atraverda is trying to do is to overcome the issue that people have with lead-acid batteries in that they tend to be bulky and heavy. So what we've done is create what's known as a bipolar battery. And that basically means that we get rid of all the inert heavy lead parts within the battery and put in our proprietary conductive ceramic, which acts as what's known as a bipole. So what happens there is you have the negative active mass and the positive active mass of the battery on the same plate. So it's a far more efficient system.
So it can be much more compact. Lead-acid batteries are what we use in cars at the moment, aren't they? And they are heavy. They're big, chunky things.
Well, absolutely. And as you were talking earlier, what you do have there, however, is a tremendous amount of power, and that's down to the number of lead grids that you have in there, creating a very high surface area. So that's what creates that power that you need in order to crank an engine.
And so what's the difference, really, between these mono and bipolar batteries? Can you get the same power from them?
You certainly can, because you have a much shorter current path. So the plates within a bipolar battery, just like Atraverda's building, are very close, whereas in a conventional product you have quite a tortuous path to get all the energy and the power from the bottom of the grids through all of the lead parts and out of the terminals. So the potential is certainly there to give you a higher power product.
So essentially you can get a great deal more power and a great deal more capacity for the same volume.
Yes, and the principal reason for that is that you're taking a lot of the heavy lead parts out, and therefore you are actually filling the space with more active parts rather than inactive parts, simply.
And we've already talked about electric cars today. Is that the sort of place you see these bipolar batteries being put in place?
Yes, it is. It's quite interesting, actually. The the whole of the energy storage markets and low-carbon vehicles is obviously becoming a hot topic. But it's interesting that lead-acid batteries have been used in electric vehicles for a long, long time. You did talk earlier on about golf carts, for instance. And in Asia, in parts of the world like China and India, what's known as e-bikes and e-scooters are absolutely booming. And because of the cost benefits of the lead-acid system, they do generally tend to be lead-acid batteries. So those are two areas which we at Atroverda feel that we can really get into, simply because we are basing our battery system, as I said earlier, on a proven chemistry, but also can take out some of the heavy lead and therefore make a smaller, less bulky product.
Well, that sounds really good, and I'm sure you will have inspired a few questions from our listeners as well. So if we can keep hold of you till the end of the show, then we'll see if anybody at home has a question for Andrew. That's Andrew Loynes from Atroverda. Then please send them in to chris@thenakedscientists.com.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Ben Valsler and me, Helen Scales. Now, electric cars are not the only option we have for sustainable personal transport. Already there are a number of vehicles on the roads that use biodiesel, and that's diesel that doesn't come from fossil fuel but from living creatures, from living plants. Now, Anna Stevenson is a PhD student at the University of Cambridge, and she's looking at alternative ways to meet the demand for biodiesel. So, Anna, hello, thanks for coming into the studio.
That's okay.
And first of all, could you tell us what are biofuels and why do we need them?
Okay, well, the idea of a biofuel is that you might be able to get it to be carbon neutral. And this is because when you burn carbon which is in a plant, it's carbon which has been stored or fixed during the life of the plant. Therefore, when you burn it, you're releasing the carbon dioxide which has been fixed during its life. And therefore, it's not releasing carbon dioxide which has been stored underground, which is what you do when you burn fossil fuels.
So that's really old carbon, isn't it? It
was
fixed millions of years ago, so we kind of don't count it anymore. But
yes,
doing
precisely.
it sort of in a neutral way by absorbing it and then releasing it in a sort of short space of time.
Yes, so it won't contribute to global warming. That's the idea, but in reality, biofuels do require many inputs, which are in the form of fossil diesel or things which have been made using fossil energy. For example, fertilisers. And also when fertilisers are added to soil, they release nitrous oxide, which is a very potent greenhouse gas. So in reality, they're not carbon neutral, but the aim is to be able to make carbon neutral biofuels.
So that's what we're kind of working towards. So I believe there was what's called the first generation of biofuels, wasn't it? And so that's really the sort of crops that we could actually eat, things that produce oil like rapeseed and soya, is that right?
Yeah.
And there were lots of problems associated with those kinds of crops, weren't there?
Yeah, there are many problems. For example, palm oil is the main oil which is used in Malaysia and Indonesia, and because of that, a lot of rainforests are being chopped down and killing orangutans, but also releasing loads of carbon dioxide and actually contributing a lot more to global warming than the actual saving you're getting from using the biodiesel. Also, there are issues to do with competition with food crops for land. So current biofuels really have a long way to go.
Yeah, there's a lot of talk about we should be using that land for fuel, for food, and that's not really a fair use of it. So I think at the moment it seems quite a lot of bad feeling about biodiesel, really, isn't there, in the press and so on.
Yes,
but we've got a second generation we're working towards, a new way of doing it. What does that involve?
Well, at the University of Cambridge, we're doing a lot of research into biodiesel from algae. Algae have got a high photosynthetic efficiency, which means that we can produce a lot of oil from the sunlight, and this oil we can then turn into a biofuel.
And so it's seaweed, is it? Like big kelps and things like that, or different types? What sort of species can we use for this sort of thing?
There are many different types of algae, but they're mainly macroalgae and microalgae species. And in Cambridge, we're mainly focusing on microalgae, which are single cells, but in other areas, they're also looking at large macroalgal species and in the form of kelp, so seaweed.
And so are they all saltwater species, or are they also
no,
freshwater?
they're both freshwater and saltwater. But obviously there's the advantage that if you're using seawater, then you don't have the issues associated with using a lot of freshwater.
Because that's another problem, isn't there, with sort of the first generation of biofuels, is that they use lots of fresh water, and that's another limited product really in the world, and we might need that for other things as well.
Yeah.
So are there other reasons why using algae is maybe a really likely way of creating good and carbon neutral biofuels in the future?
Yes, well, the other thing is that you can produce significantly more oil per hectare using algae rather than land-based crops. And this is because you're not producing like the leaves and the stalks and all these things which are associated with land-based crops.
How do we actually grow them? Sorry, I can't try and imagine.
Yeah.
Are we sort of putting them in ponds, or how are we doing
There
it?
are two main ways of growing them, either in ponds, like large raceway ponds, which that's how it's mainly grown and harvested, because at the moment algae is also used as a food source.
People eat it.
Sorry?
People eat algae?
They do, yeah.
Really? Goodness, okay.
But you can also use closed systems, which are called photobioreactors.
So big kind of just sort of great big containers,
big
really.
fish tanks,
Big fish
basically,
tanks, right.
which have got CO2 bubbling through them. And
Right.
they have the benefit because you won't have competition from other algal species, because if you've got a large pond, then other species can get in and overtake. But the thing is, you need quite a lot of material, and there's energy associated with producing that material for a tank. So there are benefits for each.
Yeah, so you really got to look at that whole balance between what you're using and what you're getting out of it. And how do you actually create biodiesel from the algae? How do you go? Presumably you can't just sort of squash it up and then put it in your car.
No. So it's the same as conventional biodiesel, which is an esterification process with methanol. So what you do is you get your algae and you grow it under specific conditions to be able to produce an algal lipid or an oil. And really what we want is a triglyceride oil.
That's a type of fat, isn't it?
Yes,
is that
a
right?
fat.
It's a
Yeah.
particular type of fat, right.
And then you have to remove the fat. And there's a lot of research into trying to do this in an energy efficient way, because the thing is there's a lot of water which is with the algae. And so we want to have an extraction process which will be able to do this energy efficiently and not have to remove all of the water in, for example, a step which requires a lot of heat.
Right, because it's all about trying to make this as efficient as possible so we can actually achieve that goal of being carbon neutral.
Yeah, so what would be ideal is if you could grow algae to have a really high lipid content of maybe 60%. And if you were able to put small holes in it and then let the oil just go out into the water and have a separate layer of water and oil. And then if you were able to extract the oil in that way, then you wouldn't need to remove all the water using fossil energy. And so then you have your oil and you use this esterification standard process to produce the biodiesel.
So these are all things we're working towards. And just very quickly to round that up, in all likelihood, when do you think we might see these actually being used, these algal-based biodiesels?
Well, really, it is in its infancy at the moment. I'd say in 10 to 15 years' time.
So not too far off, but we still got a bit of a way to go.
Yes, yeah.
That's fantastic. Well, thanks ever so much, Anna. That was Anna Stevenson. She's at Cambridge University, and she's helping to find out new ways of developing biodiesel.
Reacting to the world's best science. The Naked Scientists.
This is The Naked Scientists. We've still got our question of the week coming up, finding out in what conditions it's the best thing to do to scrap an old car and buy a new one. But we also have Anna Stevenson here in the studio with us. Anna, you've just been talking about how we can use algae to make biodiesel. But one thing you said was that we need them to be as fatty as possible.
Yes.
How do you make that happen?
Well, there are many different species of algae available to us, just naturally occurring species. And there are many species which are fast growing and many species which produce lipids. And there's a lot of research into finding the ideal species, which is both quick at growing and also will produce a lot of fat. So that's the research which is going on at the moment. There is the potential for genetically modifying different species as well, but obviously that has issues associated with it.
But it does seem that if you can find the gene that says, I make lipid and express it as much as possible in whatever species of algae you've chosen, then you should be able to make something that's really efficient and really could make an awful lot of biodiesel in a very small space for relatively little cost.
Yes, that's the plan.
Wonderful. Well, in fact, there are buses in Cambridge that run on biodiesel. I know that
Yes,
much.
there are, yes, indeed.
And I know that where I used to live in Aberystwyth, when I was a student at the University of Wales, Aberystwyth, there was at least one van that was clearly running on homemade biodiesel, because as it went past, it smelt very strongly of fish and chips.
Fish and chips. Yes, you do hear about sort of people going to the fish and chip shop and asking for old used oil and putting that into their cars, which works on a small scale, but obviously we can't do that everywhere. Otherwise, all we'd ever eat was fish and chips, I think, wouldn't it?
And we did report on The Naked Scientist a little while ago about using oils extracted from coffee to do the same thing, so that would actually smell really nice.
Oh, I'd just be wanting to drink coffee all the time, like walking past coffee shops and just feeling the need for coffee. That would be terrible.
And would the algal biodiesel smell of ponds, perhaps? Smell of nice fresh water and sunny days?
No, I don't think so, because once you've extracted the oil, then it won't have any of the algal remnants left, apart from the oil.
That's a great shame, although I'm not actually sure what algae smells like, so it might not be that bad after all.
Absolutely. Well, now it's time for our question of the week with Diana O'Carroll.
This week, we're cashing in on cars.
Hi, this is Steve from Crowborough. My question is, with the budget introducing the £2,000 subsidy to scrap old cars, I'm trying to figure out how much energy and carbon goes into the manufacture of a new car. Considering the increase in efficiency of the new car, how many miles would I have to drive to achieve an overall carbon saving?
This is called cash for clunkers in the US, but should we scrap the scrappage scheme?
I'm Pablo Pastor, and I'm Vice President of Greenhouse Gas Management at Climate Check and also a columnist at treehugger.com. So unfortunately, there is no easy answer. It really depends from vehicle to vehicle, not only the vehicle that you're currently driving that you would be replacing, but also the vehicle that you would be replacing it with. The U.S. government came out with a model for figuring out the energy used to make a vehicle called GREET, G-R-E-E-T, and basically it tells you how many BTUs it takes to build a car. The manufacturing of the average car is roughly equivalent to 880 gallons of gasoline in terms of the energy that's used. If a new car will save at least this much gas, it definitely makes sense to get rid of the old car. If we assume that your old car has around 100,000 miles left on it, with good maintenance, your new car would need to be at least 6 miles per gallon better to make up for the emissions from manufacturing. That means that if your old car gets less than 24 miles per gallon, it makes environmental sense to get a new car that gets 30 miles per gallon or better. Not only can you feel better about your environmental impact, but you also get a £2,000 discount on your new car.
So as long as you plan to put at least 100,000 miles on the clock and your new car can do 6 miles per gallon better than the old one, there will be an overall carbon saving. So obviously, if you only drive to the supermarket on weekends and plan to change your car every 4 years, it's probably not going to be worth cashing in your old car for the environment. Well, next week we'll be finding out how much energy is used in your sleep.
Hi, my name's Garvey from London, and I would like to know, why don't we sneeze when we're asleep?
So can you help us to solve our next question of the week? If you have an answer and you'd like to be included in next week's episode, then please email us. That's chris@thenakedscientist.com, or you can write the answer onto the question of the week section on our forum, which you can find at thenakedscientist.com/forum.
We also heard from Make It Lady on our forum, who said a new car has an average of 6.7 tonnes of embodied carbon, and it would take you just over a year of driving to have emitted just that much.
Now, we're not sure where she got this figure from, but someone else on the forum, Chemistry for Me, said that he'd found some slightly different stats. He said that the average CO2 emissions for new cars sold in the UK fell to a record low, so that's something we can be proud of 167.2 grams per kilometre in 2006. But that means that to reach 6.7 tonnes in a year, which is what Make It Lady seems to be suggesting, you'd need to drive 40,000 kilometres.
That's quite a lot, isn't it? I was going to say, yes, how much are you driving? I mean, I do drive a car ever so occasionally, and I don't think I drive 40,000 kilometres, even if I tried really hard.
No, I'd be very surprised, and I suspect your insurance would be very expensive as well. And next week's question is a great one, because I've been wondering this recently. I went up to Edinburgh recently, and we camped, and it was wonderful. I had a lovely time.
Very nice.
But I got bitten a lot by either midges or mosquitoes, and I've got lots of bites.
You do have lots of spots still, don't you, poor thing?
But I found that I scratch in my sleep. So I wake up and found that I've scratched my bites, but I've never woken up to sneeze. So we want your discussion on this question of the week. You can find it on the forum or at thenakedscientist.com/QOTW. We will read out as many of the really good entries as we possibly can, and we really value your contributions, and it's always great when you can provide an answer that's as good, if not better, than the expert. But that's all we have time for this week. Many thanks to Andrew Loynes and Anna Stevenson for joining us, and to Aaron Kankiwala and Greg Offer of Imperial Racing Green for showing Mira their carbon-neutral racer. Thanks also to our production team, Diana O'Carroll, Mira Santhalingam, Dave Ansell and Tom Simpkins. And finally, thanks to all of you at home for listening. Next week, Dr. Chris, Dr. Kat and I will be taking on your science questions, so do get in touch. You can write to us on chris@thenakedscientists.com with any questions, kitchen science ideas or comments. We would love to hear from you. If you want to hear the show again or catch up with old shows that you may have missed, you can download the Naked Scientist podcast for free from thenakedscientist.com/podcast. Have a great week. Goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.